The grid didn't break. No explosion, no hurricane, no storm. The transmission lines were still standing. The power stations were still running. But the people responsible for watching the system had stopped receiving the warnings that told them something was wrong. And by the time they understood what was happening, roughly 50 million people were already in the dark. What happened on August 14, 2003, wasn't caused by one spectacular failure. It was a chain of failures, physical, operational, and technological, that gradually stripped away the layers of protection surrounding one of the world's largest interconnected systems. At the center of that chain was something surprisingly small, a software fault inside a control room alarm system. This is how the power grid went blind. The North American power grid is not one machine. It is a vast interconnected network of generating stations, transmission lines, substations, protective equipment, and control systems operating across enormous distances. Electricity has to remain balanced continuously. When generation and demand fall out of balance, conditions can change rapidly. And because different regions are electrically connected, a problem in one area can place additional stress on neighboring systems. That interconnection provides resilience, but it also creates a dependency. Operators have to know what is happening. FirstEnergy operated a large transmission network in Ohio. Inside its control center, operators used an energy management system known as XA/21, supplied by General Electric. One of its functions was the Alarm and Event Processing Routine, or APER. Its purpose was straightforward. When something important happened on the grid, the system was supposed to tell the operators. A line trip, a breaker opens, a major system condition changes. The control room should know. The alarm system was effectively part of the control room's nervous system, and on August 14th, that nervous system began to fail. According to investigators' reconstruction of system logs, the alarm processing system began malfunctioning at around 2:14 p.m. It did not announce its own failure. There was no dramatic shutdown. The operator's screens did not simply go black. Instead, the software stopped properly processing the events it was supposed to turn into alarms. The control room continued operating. But one of the systems responsible for telling operators when something was wrong was no longer doing its job. The alarm processing software crashed because of an underlying software fault, and applications transferred to a backup server. But the problem had not been resolved. The backup system also experienced failures. By approximately 3:46 p.m., FirstEnergy had lost significant portions of its energy management system functionality. The deeper cause was eventually traced to a race condition inside the software, a timing-related defect involving processes accessing shared data in an improperly controlled sequence. The exact conditions required to trigger it were extraordinarily narrow. The software could operate normally for long periods. Then, under the wrong combination of circumstances, the fault could place the alarm processing application into an abnormal state. The important point was not simply that the software failed. It was that the operators did not immediately know that it had failed. And outside the control room, the physical grid was already deteriorating. Beneath transmission lines in northern Ohio, vegetation had been growing too close to high-voltage conductors. As electricity flows through a transmission line, the conductor heats and expands. That can increase sag. If a line comes into contact with vegetation, protective equipment can automatically disconnect it. That protection was working. The problem was what happened next. Every disconnected line changed how electricity flowed through the remaining network. The load moved elsewhere. Other lines carried more current. Those lines heated and sagged further. The initial line trips were caused by the physical interaction between transmission lines and vegetation. The alarm failure did not cause those trips. It prevented operators from seeing the developing situation as clearly as they should have. Earlier failures, including the Harding-Chamberlain line, had already begun degrading the northern Ohio network. There was still time to respond. The grid had not yet entered its final cascade, but the information needed to recognize the danger was becoming fragmented. FirstEnergy's operators were receiving some information through other sources, including telephone communications. But they did not have the complete picture that functioning alarm and monitoring systems should have provided. And there was another problem outside FirstEnergy. The Midwest Independent System Operator, or MISO, was also experiencing problems with its state estimator. The state estimator was designed to use real-time information to calculate the condition of the wider network. Investigators found that MISO's state estimator had not been producing reliable results for several hours before the cascade. That meant another layer of situational awareness was weakened. FirstEnergy had lost critical alarm functionality. MISO lacked a reliable real-time picture, and communication between organizations did not compensate for those failures quickly enough. The system still had multiple layers of protection, but those layers were no longer working together as effectively as they were supposed to. At approximately 3:05 p.m., the SAMA Star 345 kilovolt line tripped. This was a major escalation. A large amount of electrical load was redistributed across an already stressed network, but the final cascade had not yet begun. For roughly another hour, the system continued deteriorating. More lines failed, more load shifted. The remaining network became increasingly unstable. Then, shortly after 4:05 p.m., the rapid final cascade began. Generators and transmission lines began disconnecting as the interconnected system fractured into increasingly unstable electrical sections. The cascade spread through Ohio, Michigan, Pennsylvania, New York, New Jersey, Connecticut, Massachusetts, Vermont, and Ontario. The grid effectively broke apart into electrical islands. What had taken hours to develop now spread with extraordinary speed. The blackout affected approximately 50 million people, with more than 60,000 megawatts of electrical load interrupted. A problem that had begun as a regional reliability issue had become a continental-scale infrastructure failure. For millions of people, the consequences were immediate. Hospitals switched to emergency power. Subways stopped. Traffic systems went dark. Water and wastewater facilities in some areas lost normal operation. Industrial production halted. And millions of people suddenly discovered how much ordinary life depended on something they normally never had to think about: continuous electricity. In some places, power returned within hours. In others, restoration continued into the following days. Parts of Ontario were still being restored as late as August 17th. The economic losses reached into the billions of dollars. But the darkness was only the visible part of the failure. The more revealing story was what had happened before the lights went out. After the blackout, the United States and Canada created the Power System Outage Task Force to reconstruct what had happened. Investigators examined system logs, communications records, technical data, and interviews. Their conclusion was clear: there was no single cause. Vegetation management had failed. The alarm system had failed. MISO's state estimator had failed to provide reliable situational awareness. FirstEnergy's operational response was inadequate. Communication and coordination between organizations were insufficient. And crucially, the organizations involved did not develop a complete picture of the emergency quickly enough. The task force concluded that the blackout was preventable. There had been opportunities to recognize the deteriorating conditions and intervene before the final cascade. That is what makes the software failure so important. It was not the whole cause. It was one of the failures that removed a critical layer of protection at exactly the wrong time. It would be easy to tell this story as a simple software disaster. A bug appears, the alarm system fails, 50 million people lose power. But reality was more complicated. The software did not cause the trees to grow. The trees did not cause the software to fail. The line trips did not automatically mean a blackout was inevitable. The blackout emerged because multiple weaknesses interacted. Physical infrastructure created the initial stress. The silent alarm failure reduced awareness. MISO's monitoring problems weakened the wider picture. Operational shortcomings limited the response. And communication failures meant the remaining organizations did not compensate effectively enough. That is the real Null theory of the 2003 blackout. A complex system does not necessarily fail when one component breaks. It fails when enough other components fail to compensate for it. The investigation produced 46 recommendations covering grid reliability, vegetation management, monitoring, situational awareness, communication, and coordination. Before the blackout, many electricity reliability requirements were voluntary. Afterward, the United States moved toward mandatory reliability standards for the bulk power system, with federal enforcement authority strengthened through the Energy Policy Act of 2005 and subsequent implementation. Vegetation management requirements were strengthened. Grid monitoring and alarm practices received greater attention. And the broader principle became increasingly important. Systems that monitor critical infrastructure must themselves be monitored. Because a warning system that can fail silently creates a dangerous blind spot. This is what makes the 2003 blackout relevant, far beyond electricity. A pilot depends on instruments. A surgeon depends on monitors. A factory depends on sensors. A grid operator depends on alarms. The assumption is always the same. If something important goes wrong, the system will tell us. But what happens when the system responsible for telling you that something is wrong develops a fault of its own? A visible failure creates an emergency. A silent failure can create confidence. The screens are still on. The operators are still working. The control room still feels normal. But one of its most important protective layers has disappeared. That is what happened in Ohio. The grid was deteriorating. The alarm system had lost critical functionality. And the people responsible for managing the grid did not immediately know they had lost that warning system. Then one line tripped. Another followed. Load shifted. More lines became stressed. Protective systems disconnected equipment. And eventually, the interconnected network could no longer contain the cascade. The most dangerous failure wasn't simply the moment the grid went dark. It was the moment the people responsible for the grid lost the ability to see the darkness coming. The transmission lines were still standing. The power stations were still there. The infrastructure had not disappeared. What disappeared first was something less visible: awareness. The 2003 Northeast blackout was not caused by one tree. It was not caused by one software bug. And it was not caused by one person. It emerged from weaknesses that were supposed to be separated by layers of protection. When enough of those layers stopped compensating for one another, the next failure became far more dangerous than it should have been. That is the lesson hidden inside the blackout. A system doesn't only need to survive failure. It needs to know when it is failing. Which mattered most? The software failure, the operational failures, or the assumption that all the systems watching one another were working? Subscribe to Null Theory for more investigations into the hidden weaknesses inside the systems we trust.